previous lessons, we have looked at several health issues and used the tools of data handling to help us understand the issues. We found that the measures of central tendency of data don't always give us enough information. So although the mean, the median, and the mode tell us something about the different averages of data, sometimes a measure of how spread out the data is can be more useful. So, we looked at one type of measure of dispersion, the interquartile range. We saw that the interquartile range helped us to work out how many beds the children's ward needed so that for 75% of the time there would be enough beds. The interquartile range is worked out by dividing the data into 4 quartiles, which are separated by the median, the lower quartile, and the upper quartile. The interquartile range is the spread around the median. So, the interquartile range is developed as a measure of the spread of data with the median as its middle point. But, as we've seen in other lessons, the median is not always the best measure of central tendency or the best average to use. This is because the median is in the middle position in a set of ordered data and is not affected by the actual values of the data. In many cases, the mean is a better measure of central tendency because it gives us a more accurate picture of the average of the values in a set of data. In this lesson, we'll show you how to work with other measures of dispersion, which use the mean as the average of the data. We call them variance and standard deviation. By the end of this lesson, you should be able to calculate mean, variance, and standard deviation of a set of data and draw conclusions about the data from the mean and the standard deviation. We've spent quite a lot of time in this series looking at statistics about people who are ill and who need to be in hospital. Today, we're going to have a look at some statistics for healthy people. We want to see what pulse rate a healthy teenager can expect to have. A person's pulse rate, also called a heart rate, is a measure of the number of times their heart beats, or pulses, per minute. You can feel these beats at certain places on your body called pulse points. You can estimate your own pulse rate if you want to. Feel the inner wrist until you find a point where you feel the pulse. If you struggle to find it there, you can also try to find it here on your neck. Press down on this point and then count how many times you can feel the beat over a minute. You will need to time yourself with a stopwatch or something that shows the seconds. I've based the data we will use on some research done by the Department of Health. They collected their data from survey questionnaires completed by over 2,000 young men and women aged 15 to 19. I'm sure you'd like to know what an average pulse rate is for someone of your age. So I will start with the data for 20 18-year-olds. We will use these to find the average pulse rate. When the data values are measurements, the mean is usually a more useful average than the median. The mean considers the value of each measurement and not just its position in the list of data. Do you remember what the mean is? The mean is the total of all the data values divided by the number of values that you have in your data set. So, I can add all these values together. That's 71 plus 71 plus 72 plus I get 1,510. We've added 20 numbers together. Now we divide by 20, and that is 75,5 beats per minute. So, the mean of the data is 75,5. Was your pulse rate somewhere close to this? What we are going to look at now is how spread out the teenagers' pulse rates were from the mean. We find this using a measure of dispersion called standard deviation. It measures what the average or standard amount is by which the data values deviate from the mean. Usually, standard deviation is measured when you want to find out by how much a large set of data differs from the mean. Are all the data values clustered close to the mean, or are they spread out? How different, on average, is each value in the data set from the mean? There's a set mathematical way to calculate this, and we need to go through the steps carefully. I want to show you how to find the standard deviation using just a few easy numbers. Then, after we've used this method, we can apply it to the data set of pulse rates that we have here. Suppose 4 children are 6, 8, 5, and 9 years old. To find the mean of their ages, we can add them together and divide by the number of children, which is 4. So, the mean is 28 divided by 4, and that's 7. To show what we've done here as a formula, we write the sum of using this sign called sigma. Sigma is a Greek letter used as a short way of saying the sum of. X represents the data values, which in this case are 6, 8, 5, and 9. Then, to show that we've divided by the number of values in the data set, we divide by n, which in this case is 4. The answer we have found is the mean, and we use x bar to represent the mean. Now, we want to see how different each age is from the mean. 6 is 1 year younger, 5 is 2 years younger, 8 is 1 year older, and 9 is 2 years older. So we have found x minus the mean bar x for each data value. So x minus x bar shows how far away each data value is from the mean, or by how much it differs from the mean. When we've got a lot of data, knowing how much each value differs from the mean doesn't help us. A more useful measure of how spread out about the mean the values are is the average amount by which each value differs from the mean, or the mean of the differences from the mean. So far, we've seen that the mean is the total of all the values divided by the number of values. So let's start by finding the sum of the deviations. -1 plus 1 minus 2 plus 2 comes to 0. Actually, we'll get 0 as the total of the differences for any set of data. This doesn't help us to find the mean of the means. To avoid getting a 0 answer, we choose rather to find the square of each deviation. Don't worry about what the squaring does to the sum. Later in the calculation, we'll cancel the effect of squaring the numbers. Have a look. -1 squared is 1. 1 squared is 1. -2 squared is 4. And 2 squared is 4. We add each of the squared differences from the mean together, which for our data gives us 10. Then we divide by the number of values, in our case 4. So we divide 10 by 4 to get 2,5. The number we've found is called the variance. It's a measure of dispersion around the mean. The variance is the average of squared differences from the mean. So, we find the sum of the squares of the difference between each value and the mean, then divide that by the number of data values. The variance is based on square numbers, and we want to know how spread out the ages are in years, not in square years. So, we take the square root to get back to numbers of years. To deal with this, we find the square root of the variance. We call this the standard deviation. Look at the children's ages again. The variance was 2,5. If we find the square root of this, we get 1,58. What we found here is the standard deviation for the 4 ages of the children. This tells us that the average amount that the 4 ages deviate from the mean of 7 is 1,58 years. Now we can go back to the pulse rates. To find the standard deviation in this set, we first find the mean. We found earlier that it was 75,5 beats per minute. Then, we need to work out by how much each of these values differs from the mean. Let's make a table to record all our findings. We'll call this one deviation from the mean. The first value is 71. 71 minus 75,5 is negative 4,5. The next one will also be negative 4,5. Let's continue filling in all these values, and the last one is 81 minus the mean of 75,5, which is 5,5. To look at how much these deviate from the mean, we want positive values, so we square each value. We'll do this in the next column of the table and label it deviation squared. So, for the first one, negative 4,5 squared comes to 20,25. After working all of these out, we can add them together to get 423. So, the sum of the squares of the deviations is 423. The next step is to divide this sum by the number of data values. The pulse rates were taken for 20 teenagers, so we can divide by 20. And that's 21,15. This is the value for the variance. But this is a sum of squared values, so the square root of this value will be more useful to us. All the data values were squared. Now we must find the square root of our sum. The square root of 21,15 is 4,6 pulses per minute. What we found here is that the mean pulse rate is 75,5, but that on average, the pulse rates vary from that mean by 4,6 beats per minute. That shows us that there is quite a large standard deviation. It also says that on average, the teenagers in our sample have a pulse rate that lies between 4,6 below 75,5. That's just less than 71 and 4,6 above 75,5. That's just over 80 beats per minute. When we find that the standard deviation is quite big, we can question whether our average is all that useful. The range of our data is from 70 to 81, and the standard deviation doesn't really give us more information than this. I've had another look at the data and decided to separate the data into 2 groups: girls aged 18 and boys aged 18. There are exactly 10 boys and 10 girls. Once you understand the steps used to find standard deviation, you can use a calculator to do the number crunching for you. Most calculators have a stats mode and keys to work out standard deviation. I'll leave you to work out what keys to press on your calculator, but we will put examples of the key sequences in our Mindset Learn lesson notes. I started with the data for the girls. I worked out the mean and the variance of each value from the mean in this column. Then I squared each difference, added them all together, divided by 10 this time, and finally found the square root of this answer. What I found is the standard deviation for the average pulse rate for the girls. Then I found the standard deviation for the boys. This gives us quite a different picture. For the boys, I found that the mean is 71, quite a bit lower than the previous mean, and the standard deviation is only 0,89. For the girls, the mean is 80, and the standard deviation is 1,0. So, by separating the girls' data and the boys' data, I now have two different means, and the standard deviation for each one is quite small. This smaller deviation suggests that we have probably found a trend that is true for a bigger population of boys. For most boys who are 18 years old, their pulse rate tends to be about 71 beats per minute, or within 0,89 of this. For most girls who are 18 years old, their pulse rate tends to be about 80 beats per minute, or within 1 beat of that. What conclusions can we draw from this about pulse rates? Lower pulse rate is usually associated with being fitter. So it looks as if boys of this age are generally fitter than girls of this age. But we would have to investigate other biological differences between boys and girls before we can make this conclusion. What we can say is that girls should evaluate their fitness against a fit heart rate for girls, and boys should evaluate their fitness against a fit heart rate for boys. As I said earlier, I've based these statistics on research done by the Department of Health. Their findings for 18-year-olds were based on a random sample of 213 girls and a random sample of 207 boys. Their sample is taken from different provinces of South Africa and from different population groups. Here are some more interesting statistics from this research. The research was completed on 1,054 adolescent males aged 15 to 19 years old. When the data was grouped according to population group, the following means and standard deviations were found. The 852 African males surveyed had a mean mass in kilograms of 55,4, with a standard deviation of 0,39. The 73 white men surveyed had a mean mass of 66,8 kilograms, with a standard deviation of 2,15. From this research, it would appear that white men are heavier than African men, and that they deviate from the mean by more than 2 kilograms. So, white men aged 15 to 19 years old have a mass of, on average, between about 64,7 kilograms and about 68,9 kilograms. African men weigh more than 10 kilograms less than white men of the same ages, and their masses deviate from this mean by less than 400 grams. We can't really make conclusions from this data without looking at the heights of African men compared to white men. This was also included in the research done. From the table, you can see that African men have a mean height in meters of 1,65 with a standard deviation of 0,36. The white men have a mean height of 1,76, which is about 10 centimeters taller than the African men. The standard deviation for white men is also greater at 1,32. Well, that gives us something to think about. But many factors might contribute to white men being heavier and taller than African men. Researchers would need to look at the nutrition and the income of the families that these teenagers come from. They would also need to see whether their sample is big enough. Did you see that only 72 white men were surveyed compared to 852 African men? Sometimes a smaller sample can result in a bigger standard deviation from the mean, as was the case with the white men. Another useful statistic is the measure of body mass index, called the BMI for short. It is calculated as the mass in kilograms of a person divided by the square of their height in meters. So, let's find the BMI for a person whose body mass is 60 kilograms and whose height is 1,7 meters. It will be 60 divided by the square of 1,7. In this research, the mean of the BMI for African men was 20,4 with a standard deviation of 0,14. The mean of the BMI for white men was only a little higher than this at 21,4 with a bigger standard deviation of 0,54. This could indicate that although the white men have a higher nutritional status than the African men, the difference between their nutritional statuses is not as big as it appeared when we looked at height and mass as separate measurements. Let's look again at what we've learned about our new measure of dispersion called standard deviation. First, we saw that it can give us a better measure of the spread of data than the interquartile range. This is because it considers the values of all the data, not just the positions of the data. Then, we worked with the steps needed to calculate standard deviation. First, we needed to find the mean of all the data by finding its sum and dividing by the number of values in the data set. The next step was to calculate how much each value in the data set deviates from the mean. Then, to eliminate the effect of the negative signs, we squared each of these deviations and added the deviations together. We took this sum and divided it by the number of values, n. The answer we came to from this sum is called the variance. Finally, we found the square root of the variance in order to counter the effect of squaring each difference earlier on. Now it's your turn to work with standard deviations. Record the heights of the learners in your class and find the mean, the variance, and the standard deviation of your set of data. Join us soon for our next lesson on scatter plots.